Hello, class. In the very first lecture, we have seen this particular condition here listed on the presentation slide. Now, at the time, we didn't really say too much about it. We just said this is a very important condition and something that we need to understand to make use of. Now, in this lecture, we're gonna take a closer look at this condition here. The usefulness of this condition is that if we were to be able to take this condition here, and we can very easily derive the Black-Scholes formula. Now, the approach we're gonna take today is that we're gonna take this condition as true to begin with, and we show that this will, if we use a log normal process for our stock, then this will lead to the Black-Scholes-Merton formula be derived. Now, and then we show that this condition is true by going through an actual integration. Now, if we have a call option, let's just take the very simple case of a non-dividend pay, an option on a non-dividend paying stocks, okay? And say that stock follows this log normal distribution here, log normal process here. Recall this is in the real world because we have a drift mu here, okay? And then if the condition is true, we would be needing to calculate some expectation here in our pricing approach. Now, you take a close look at this pricing approach here. So what we're saying here, we're saying the call price is really a discounted expected value, expectation here, of a function where this max function here is really the payoff function at maturity time t. So we're saying the call price is the discounted value of the payoff at maturity time. Now, this is only true at risk neutral because in this pricing valuation here, we're only taking expectation, right? We're not, accounting for any other risk-related component. So as long as you have a higher expected value, you will get a higher price. But in real world, that's not the case because even if you have the same expected value, but if one investment has higher risk than the other, for example, if that investment has much higher volatility, then the investment with the higher volatility would tend to get or require a higher compensation. So for those ones, they will have a higher price to compensate for the higher volatility. So in real world, we just can't take simply just the expectation to arrive the price. But if people are not do not consider any risk, so if people are risk neutral, they don't care about risk, then we can just simply take expectation to derive the price. So in this case, we cannot use the expectation under the real world probability measure. We must take expectation under different probability measure. And we're gonna talk about what's the difference between the probability measure under the real world versus the probability measure under the risk neutral world, okay? But suppose there exists a probability measure that is different from the real world probability measure, but allows you to derive a price of a call in this particular fashion, which means suppose there exists a risk neutral probability measure, then under that probability measure, we will have this particular condition that's true. Because if you look at this thing here, this is true for any probability measure that you're taking expectation. So you can take expectation under the real world probability measure, this is true. But if you change the probability measure to a risk neutral probability measure, this will remain true as well. So now what you would need here is, in order for this to be true and you do have the price calculated, you would need to have a value of the expected value of the stock price under risk neutral at maturity. So you need a risk neutral expectation of the maturity price of the stock. The other thing you would need is you will need a this W here, right? So this W is the standard deviation of log X. So basically, this W is the standard deviation of the log ST. Okay, so now how do we get those values? Okay, so let's look at the other the slides here to see what is ST and what value of W that we must take. Now, if you take ST, the expected value of XT under risk neutral, to be S naught ERT, and W be sigma times square root of T, then if you utilize this condition here, just plug in this S naught times e to the power RT to here. So this thing becomes this. And what you will have is this part and this part will become 1. You will multiply through, so you had S naught ND1 minus K e to the power of minus RT ND2. And D1 will get to exactly this form, and D2 will be this form, which are exactly what you have seen in the Black-Scholes Merton pricing formula here. So if this is true and this is true, then you will be able to have that risk neutral. Sorry, you will be able to have that Black-Scholes Merton formula here. Now, why are they true? Well, if you look at the process that we have talked about, so if we specified that S, the stock price, is following this process in real world, by Ito's lemma, we will know that the log S is actually following this particular process here. We can easily derive that, right? So this mu is the mu in this process here, okay? And the sigma is the sigma here. They're all both parameters. Now, in the risk neutral world, the things are not growing at mu. Everything in risk neutral is growing at the risk neutral rate of R. So in this case, we have to replace this mu under risk neutral when we change the measure from the real world measure to the risk neutral measure. We have to change mu to R. So in the risk neutral world, or when we take expectation under the risk neutral probability, the distribution is actually this, where you replace mu with R. And if you have log ST in risk neutral, it's distributed this way, having this particular distribution, then the expected value of xt, so expected value of the stock price at maturity, then is based on this distribution is S naught times e to the power RT. Also, W, which is the standard deviation of log x, which is, in this case is the log of st, then has the value of sigma times square root of t. So we actually have seen this in our first lecture as well. So if you recall, there's a presentation slide that is like this, and we looked at all the different distributions that you can actually derive if you have the log normal process. So you can look at what the log is distributed and what the value is distributed. So the value, then the expected value will have this, and the variance will be sigma squared t. So the standard deviation will be sigma times square root of t. And here, because we're doing it under the real world distribution, that's why we have a mu here. But in risk neutral distribution, we replace mu with r. Okay, so now why we have to replace mu with r? Well, because in the real world, risks are compensated. So different asset depending on their quality, they will have a different risk characteristic. They will have a different growth rate, which compensates for your risk. The stock with a higher risk, that's compensated by the market. Higher risk that the market believes that it has, the market will compensate it with a higher growth rate. The stocks with a lower risk will have a relatively lower growth rate. But in the risk neutral world, there's no such thing. So every asset must grow only at the risk-free rate, because there's no differentiation between which asset is riskier, which asset is less risky, because that distinction does not matter in the risk neutral world. So under the risk neutral world, there's not going to be any compensation for an asset having a higher risk. So they all are rewarded by the same return, which is the risk neutral return. Now let's take a look at what really is the difference between risk neutral probability and the real world probability. So if we look at here, I've drawn on the right hand side, the real world probability distribution here, right? It's the log of the stock price is normally distributed. Whereas this is the mean of the distribution, which has the mu as the growth rate here. And if the stock, if the market believes that this particular stock has a higher risk than the risk-free, well, it will always have higher risk than the risk-free, then the growth rate here, mu, is higher than the risk-free rate r. Okay, so this expected value of log e mu t, this expected value of this distribution, this log e to the power of mu t s naught, is higher than this part if everything is growing at the risk-free rate. Now, in the risk-neutral probability distribution, the mean is actually here, which is the lower point here. So the difference between the real-world probability distribution and the risk-neutral probability distribution is that you can really think about shifting the entire curve here to the left, whereas a lower value will have a higher probability here. the lower value of the log ST. So essentially, if you think about it, you would take expectation, the expectation of ST under risk neutral will have a lower value than the expected value of ST under the real world probability, because R is smaller than mu. So, and the difference is what the market is compensating you for. So if you know the risk neutral rate of return, you can just utilize this particular approach and substitute in this R as the growth rate, and you can take expectation under risk neutral, and that expectation will give you the actual price of the derivative asset. And you will see that that price of the derivative asset is then lower than just simply taking expectation under a growth rate of mu here. And the difference between that is really the market compensating for that particular derivative asset taking risk.